All right, we're back. We're actually going to be on page 319, but I thought it'd be good to start on the bottom of 318 because 319 immediately references it, right? So we identify the regions where the tangent line is above the curve, and we know from casual conversation that that means that the curve is concave down on those intervals. And then we identified where the tangent line lies below the curve, which again we know means that the curve is concave up. So now what we're going to do is kind of formalize that idea and talk about a lot of ways in which that applies. So concavity is basic. So tangent lines tell you the slope, right? The slope of the curve, slope of the tangent line, they're the same. Concavity sort of tells you how the slope is changing, right? So the slope tells you how the curve is changing. Concavity tells you how the slope is changing. So is the slope of the curve increasing? Is the slope of the curve decreasing? That's one way of thinking about it. So in fact, when we talk about concavity, there are several ways in which you need to be familiar with it, right? So the first one is if we have the graph of f prime. So you already know if you have the graph of f, you can actually figure it out. So that's, for some reason, it's in the next box instead of this box. This is the most common by like a million years. Most common by a million times. I don't know, not even a million times. Like this is 3 times more common. I don't know, I'm just making stuff up. This is most common. Most common. Okay, so the most common thing is to be given the graph of f prime. If you are given the graph of f prime, you can tell concavity of f of x. How can you tell that? You can tell because, let's highlight, f is concave up if f prime is increasing. So if f prime is increasing, that means its derivative, f double prime, is positive. If f prime is increasing or f double prime is positive, f of x is concave up. So that's one thing. If, or you can tell that f of x is f of x, the original function, concave down, if f prime is decreasing. If f prime is decreasing, f double prime, the second derivative, must be negative. Either of those scenarios, either f prime knowing either of those, f prime is decreasing or f double prime is negative, will tell you that the function is concave down. Okay, so the most common thing is to have the graph of f prime. That's why I wanted to start with that one. We already know, because we've talked about it kind of a lot, is that a function is concave up. If a function is concave up and you draw some tangent lines on it, then the tangent lines are definitely below the graph. So that one feels counterintuitive until you just like let your brain accept it. So concave up, so x squared is probably the most famous concave up curve. Draw some tangent lines, they're definitely below. So concave up, tangent lines below. Concave down, then the tangent lines are going to be above the curve. Negative x squared is maybe the most famous concave down curve. I like to think of the graphs of sine and cosine because they switch concavity, and so you get to see like a lot of really useful things. The most direct way, and this is if you have a function in particular, if you're given f of x and you can calculate f double prime, then just go ahead and do it. And then we can get concavity from f double prime. So if f double prime is greater than 0, which would mean that f prime is increasing. So f prime increasing, f double prime positive, either of those mean f is concave up. On the other hand, if you can calculate f double prime, if it's convenient, do it. And then we can kind of do a sign chart for f double prime, like just go from there. If f double prime is negative, that means f prime is decreasing. So either of those, f prime decreasing, f double prime negative, connect those in your head. That's why I'm saying them over and over. That'll tell you that f is concave down. All right, so let's actually do a problem and see if we can kind of work it out. And you'll see this is really familiar, right? Excuse me. So if you've been doing first derivative test, this feels really familiar. It's not called the second derivative test though, which is kind of weird. So let's find our point. So let's find our second derivative. So there's no like cheat to get straight to the second derivative, which is sort of annoying. Like you have to find the first and hopefully get it right, you know, because we wouldn't want to get it wrong. Okay, so 4x cubed plus 18x squared plus 24x plus 8. I think that's good. F double prime. Okay, 12x squared plus 36x plus 24. That's definitely factorable. 12x squared plus 3x plus 2. I was going to put 4 plus 2. And that's 12x plus 2, x plus 1. Got it. Okay, so that's f double prime. You know what I'm going to do? I'm going to do a sign chart for f double prime. So here we go. So this is part of why it's really important that you label them f double prime. -2, -1. Because half the time you're going to have a sign chart for f prime and f double prime. And you're going to use both of them in combination to decide where a function is. Increasing concave up, increasing concave down, and so on and so forth. So that's why we want to label them. That's also why I put so many pluses and minuses. So like regions are really clear when I like combine them all. Quadratic that opens up is our second derivative. So I know it's going to go plus, then minus, then plus. Okay, so if the second, I'm looking for state, what am I doing? Concave up. Okay, concave up means that the second derivative is positive, the first derivative is increasing, but since I have the second derivative, I'll just find where that's positive. So let's say f of x is concave up for x less than -2 and x greater than -1. And we want to say why. Why is that true? So sign charts aren't enough because f double prime of x greater than 0 on those intervals. Okay, so we answered the first part of the question. So those are the intervals where f double prime is positive, which means f of x is concave up, which you can definitely abbreviate as CU. Now what we want to do is find the actual points on the graph where the concavity changes. So I guess they're not that bad. I'm inclined to kind of use like a calculator for that, but let's do synthetic substitution instead. So -2, and then it'll be 1, 6, 12, 8, 1. You could also just sub it in. Like, it's really not that bad, but like I like to review this whenever I can. Drop down, multiply, add down, multiply, add down, multiply. That's interesting. Add down, so I just get 1. Is that right? See, I'm not doing that. Well, you get like a -48 and a +48. Those are gone. You get a -16, a +16, and 1. Yeah, wow, okay. So f of -2 equals 1. And then for 1, no, -1? -1's easy enough. So f of -1 is going to be 1 minus 6 is -5, plus 12 is 7, minus 8 is -1, plus 1 is 0. So that's weird. Okay, so the points on f of x are -2, 1, and -1, 0, bizarrely. Okay, so these points are actually, they're the points where the concavity changes from concave up to concave down to concave up. Those are the points where it changes. These are called points of inflection. Points of inflection. And it's just where concavity changes. So they're kind of neat. Graphically, I think they look really neat, usually. They're very satisfying. They're like, it's where you like plateau for a second, or where things get like really bad really quickly. Let's see. So I'm going to add a new problem, and on a calculator page, I'm going to define, I don't actually need that. I mean, I always do it, but like, let's just insert the graph page and like go from there. So it's x to the 4th plus 6x cubed plus 12x squared plus 8x plus 1. Okay, so let's see. So I'm going to trace menu 5. I want to trace until x is -2. And if you hit enter, when you do that, it'll like leave the point there. And then -1, and I'm going to hit enter, and it'll leave the point there, and then press escape. So I get these 2 points. These, if you look at it, are definitely where, let me zoom box so it looks a little better. These are definitely where we're changing concavity. So how can I tell that a little better from this? Let me do menu 8, option 1. I'm gonna put a tangent line on and just like click, click. Okay, escape. And then, yeah, there's an equation. I don't really need the equation because what I'm interested in, hide that, is if you grab the end, you can like make it longer. I don't recommend this, by the way, on the handheld. Here, the tangent line is below, which means the curve is concave up. When I get to exactly this point, suddenly the tangent line is below on one side and above on the other. That's a point of inflection. I move past and it's above, so concave down. The function's concave down because the tangent's above. Here it's on both sides again. And then here the tangent line is below. So when I say below, I mean like when you're really close to the point of tangency. And it's just gonna stay there. So concave, f of x concave up, f of x is concave down on this interval, and then concave up on this interval. Another thing your calculator can almost always do, in analyze graph, there's actually inflection point as an option. You just have to choose, so here to here, and it gives it to you, and then we could do it again. Menu 6, and then option 5. I do not use this very often. Here to here, and it finds the inflection point. So there you go. So we did it. We finally formally are talking about concavity. We've been talking about it for like, I think several sets of notes because I can't resist. But that's it. So I'm gonna cut this video here and come back in the next one and talk about it even more. So I will see you then.